All right, so there's the last little bit. I'm sorry, I'm chopping these videos up, but the new screencaster I'm using is not as efficient as smartboard technology. All right, so in these types of curves, you're able to choose your own indicator. So the way you would choose your indicator is based on the pKa value of the indicator. So if you know the Ka, then you find the negative log of the Ka to get the pKa, and then you choose an indicator where if you do plus or minus 1 of the pKa, it's equal to the equivalence point of your acid-base titration. So in this first example, it's a little high right there, but if you go between the vertical section about halfway there, in this case, halfway between the vertical section is pH of 7, so you would choose an indicator that changed color between 6 and 8. So you choose an indicator that has a pKa of 7 plus or minus 1. So how would you choose an indicator? You have to have something like this that will tell you what the indicator's values are and what pHs they change color at. So you've actually did your lab where you have a really good understanding of where they change color, and some things are a mixture of multiples of these, like universal indicator. It's a mixture of about 4 different indicators. That's why it has such a rainbow effect, and it doesn't have only 2 colors. It's because it's a mixture. So if you can choose one that has a definite color change, like say for example phenol red changes at about a pH of 7, and then one that you're also very familiar with, phenolphthalein, changes at about 8. So that would also be very good for that previous example. So going back, you've also got this other curve where you can see that some of the iconic things I told you about. For weak acids, you've got the little loop or curl area at the bottom. That's iconic of your weak acid titration. And then your buffer region here, where the pH is staying relatively constant. It is a buffer region, so you will see some pH changes, just not drastic pH changes. The equivalence point, yet again, is between the vertical section in the middle. This is closer to the 8 or 9 region. So you have to choose an indicator where your pKa plus or minus 1 will be 9, about 9, plus or minus 1. So if you chose an indicator, you would take the Ka negative log of that, find which one would match your situation the best. So here's that again. You'll notice a couple of these that you're already familiar with. On the AP exam, they will give you a bunch of unknown indicators, maybe like bromocresol purple that you've never seen before, or bromocresol green, which you've never seen before, but they'll give you the Ka values. And so if you know the Ka values, then you can definitely choose the correct one by taking the negative log. Last bit here, there's one very, very important point. This is one of those little hints that not everybody knows in the AP exam. One hint about what point our pH equals our pKa is we already know that for pH to equal pKa, that for example, weak acid concentration has to equal the conjugate base concentration. So this is our weak acid, this is our conjugate base, because in our Henderson-Hasselbalch, if these two concentrations are equal, or moles are equal, then that ratio is 1, log of 1 is 0, therefore pH equals pKa. We already know that, but now we have a word that we call that. We call that the half equivalence point in a titration. That's because there's been enough strong base added to neutralize half of the weak acid. So if you can neutralize half of the weak acid, then you are going to create that same amount of that conjugate base, which is called the half equivalence point. So if your equivalence point occurred at maybe pH of 7, but you used 50 milliliters of your titrant, then your half equivalence point would be at 25 milliliters. So this is where your equivalence point was. So you can find the half equivalence point really truly by just looking at the graph and going halfway up to where the volume added was where the equivalence point occurred. So that's one of those helpful hints that are really will speed up your process of solving problems. Last couple slides here are just some different titration curves you've not seen. We've done acid, 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 and then we've added our base, but we haven't seen many where you start off with your base and you add your acids. Some of those iconic things, once again, notice the difference between the two starting points. We're starting off at 13, we're starting off at 11.5. 13 is going to be our strong base, 11.5 is going to be our weak base. And then the loopy thing again, the loop or the curl is indicative of a weak something. In this case, it's a weak base. Also, our equivalence points are different. The strong has an equivalence point at about pH of 7 here, which is to be assumed because it's a strong acid, strong base titration. But the weak the vertical section starts down much lower and ends at the same point, the equivalence point here is about a 6 or maybe a 5.5. So your equivalence point is lower because the strong acid is stronger than the weak base, which causes the pH to drop more drastically as strong acid is added to the reaction vessel. So those differences are very similar. There's a video after this that I'm going to let you choose to watch. It's the notes that I printed for you that are kind of, it starts off with a cartoon. It's a really good video from the North Carolina School of Science and Math, and it's another lady, she's a Navy chemistry teacher. She goes through these differences that you should see on the graphs readily. So if you have time, I really highly recommend you watch it. You can use it for study evidence. You can also take notes on the paper I gave you or read through the notes I gave you. Last couple things here. I've already gone through multiple examples of how to solve acid-base titrations where you start with the acid. This one's exactly the same thing, it's just we're going to start with the base. If you start with the base and you want to know the pH at the very, 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 very beginning, before you start titrating at all, you have a weak base, you do an ice box, you find the OH concentration, you find the you find the pOH and then the pH. If you have a point where you're not to the equivalence point yet, but you've added strong acid, you have a reaction between an acid and a base still. So you would make a before, during, and after box, and you would have, this is kind of like partial neutralization, where you have some of the ammonia, in this case, left over, and you have created some of your ammonium or your conjugate acid. That's when you're able to use your Henderson-Hasselbalch equation, but making sure that you're using your Kb, so you'd probably be solving for your pOH, not your pH here. At the equivalence point, that's where this amount is going to be equal. So all your NH3 has reacted. You've allowed for the formation. I'm sorry, not this. It's for your NH3 to equal your H3O plus added are equal. In this case, you've created only your salt which has that ion that's going to act as an acid. The ammonium cation can donate to the water, which is going to form your hydronium, which is acting as an acid, so you'd find the Ka for that, do an ice box, and roll with it, find the pH. Last little bit is after the equivalence point has been met, and you keep adding strong acid, the strong acid is the only thing present that's going to actually be controlling your pH. So you just take the negative log of your H plus concentration. Oh, and remember, this is per your total volume at that point to get the pH of that solution. Last curve is a diprotic curve. Diprotic means you've got two hydrogens that are ionizable. So in this case, it's got two equivalence points. You can see these very clearly at the vertical sections, about halfway up the vertical section. So in this diprotic acid, the first deprotonation occurs here. So the first H plus pops off there, and then the second H plus pops off here. So it takes a lot of base, and in this case, sodium hydroxide added to deprotonate the first time and then to deprotonate the second time. The only time you're ever going to see these two very distinct equivalence points are if the Ka1 and Ka2, or if you had a triprotic Ka3, were vastly different. They're very, very different in their maybe like 10 to the negative 2 or 10 to the negative 8. So they need to be very different. If not, it looks like something kind of like a wavy line. So if it looks like that, it's really hard to tell where the equivalence points are, and that's because the Ka1 is very similar to the Ka2. So that's going to be something that's very hard to tell the equivalence point of, but most of the time I'll try to choose very good diprotic acids that ionize vastly in different pHs. And we'll do some more problems with diprotic when we get back. Alright, that's it. So keep working on these. Hopefully you went through and did all the problems with me. I appreciate your patience with all the videos.